welcome you all for the day 3 of Atal MDP on the topic Power Electronics Application to Renewable Energy System, Electric Vehicle and Intelligent Control, which is scheduled from 10th to 21st October 2022 in hybrid mode. Today's our distinguished speaker is Dr. M. Balaji, Professor, SSN Engineering College. His short bio will be read by the co-coordinator, Ms. Sasikala A, followed by the session. Ma'am.
Yes, sir. Good evening, all. Today's speaker is Dr. M. Balaji. He is Associate Professor in the Department of Electrical and Electronics Engineering. He has 18 years of teaching and research experience. He received his BE degree first class with distinction from Annamala University, ME Power Electronics and Drives from Sri Venkateswara College of Engineering with 5th rank, and PhD in the area of Special Electrical Machines from Anna University. He has published 25 papers in international journals and around 30 papers in national and international conferences. He has coordinated a national level conference, 4 national level workshops, and has delivered guest lecture at various conferences and workshops. He is a recognized supervisor for Anna University. He is currently guiding 4 PhD scholars working on design and control aspects of electrical machines, hybrid electric vehicles, and power converters. 5 scholars have completed PhD under his guidance. He has completed DST SERV project titled Design and Development of Hybrid Switched Reluctance Motor Drive 2015 to 18 with rupees 22 lakhs under fast track scheme for young scientists. He is the co-principal investigator for the project titled Design and Development of Permanent Magnet Assisted Reluctance Motor Drives for Pump Application, funded by Science and Engineering Research Board, worth rupees 22 lakhs. Here, your session starts now, Dr. M. Balaji, sir.
Thank you, ma'am. Thank you for the intro. I'd like to thank Dr. Muttamilan sir for Sairam Institute of Technology for giving this opportunity to share my experiences in this particular field. So I'd like to focus on the fault diagnosis of electrical machines in EV applications. So I have organized my lecture as in this particular order: classification of electrical machines, what are the faults that take place in electrical machines, how we can diagnose the faults in electrical machines, and with respect to specific applications, we have done some work in BLDC motor drive and SRM motor drive, particularly with respect to fault diagnosis, and how machine learning can be integrated with the fault diagnosis approach. So this is the overview of my presentation for today. And this fault diagnosis technique, it can be applied even for a general case. General case in the sense, the methods can also be used for whenever you are going in for a microgrid, when there is a fault in a microgrid, or for any applications, you can follow a similar approach. So I have taken electrical machines, I have sensed those parameters, but the general procedure, what we'll be discussing today, it can be used for the different applications. Can be used for different applications, and especially when with this machine learning and data analytics coming up, we can explore newer algorithms and see how effective we are going to detect the fault diagnosis and all those things. So it's a sort of exploration that we can take it. So a brief introduction why we go for EV. This has been we have been deliberating on this for past few years. Okay, for obvious reasons we prefer electric vehicles, and these are all the reasons why we prefer electric vehicles. And when you see the structure of electric vehicles, okay, we call them as a pure electric vehicle or hybrid vehicle, hybrid electric vehicle. There are more topologies in that. So when we see the structure, this is the general structure of an electric vehicle. So I just like to take the pin. So this is the general structure of an electric vehicle. We'll have a battery pack. We'll have a battery pack. From the battery pack, we'll have a DC-DC converter which will be feeding the inverter. Okay, this is our inverter, and then this will drive the traction motor. The traction motor is in turn coupled to the wheel mechanism. So this is what we call it as a mid drive, or what we call it as a belt driven motor, or coupled with a gear. And another type of electric vehicle is what we call it as a in-wheel electric vehicle. We call it as a in-wheel electric vehicle, wherein the electrical motor is fitted in the wheels itself. So that is one more topology. So this is the general structure of the electric vehicle. And especially if you take the motor part plays a very vital role, as we all know. When we take the motor part, there are a lot of developments that are taking place in this particular aspect, especially in the control aspect of these motors. And there is a constant exploration in the design of electrical motors as well, and control aspects of electrical motors as well. There is a lot of work which is being going on, how to enhance the performance. And then while we are interfacing it with a battery pack and with a DC-DC converter, there is a lot of scope for work in the DC-DC converter and the inverter topologies as well. And it is when we take today's topic as fault diagnosis, the possibility of fault can occur. There is a possibility of fault to occur either in electric motor, okay, or in the converter as well. So there are different possibilities where the fault can occur. Okay, the one potential area where you can explore is the traction motor. Other is the converter faults also we can consider, and how to diagnose those faults, and how to identify when there is a fault, how to diagnose it, and how to take the corrective action. So taking corrective action is more important, and to have a reliable operation of the drive. So this is the structure of the electric vehicle, the general structure. And as I said, when you take the electric motors, okay, we have a different numerous choice of electric motors. So we can, general classification is we classify the motors as AC motors and DC motors. Here there are different classifications. And then here, when you see the AC machines are classified into asynchronous machines and as well as synchronous machines. And we know that the so-called synchronous machines have thrown up an area of what we call it as special electrical motors. The origin of, or the structure, I can say, the structure of the special electrical motors have emanated from your synchronous motors. So that is why they have classified the special electrical motors under the category of synchronous motors. We can have a category as brushless DC motors, or a pure permanent magnet motors. We can have a series motor. We can have a stepper motor. We can have a reluctance motors. So these are all the wider configurations of motors which have been constantly explored for not only for EV applications, for all the other applications. All these motors are explored, and especially again there is again a work which is also done in the case of your induction motors. Equally, induction motors as well as PM motors are also being explored for electric vehicle applications. And a newer category of this breed of motors, what we call it as a synchronous reluctance motors. These motors are also being widely explored in addition to switch reluctance motors, which work on the reluctance principle. Now, why there is an interest in induction machines, why there is an interest in switch reluctance and synchronous reluctance motors is, whenever we go for permanent magnet, the cost of permanent magnet and the availability of permanent magnet is going to be a challenge. Availability of permanent magnet is going to be a challenge. So that is why there has been a constant exploration of going in for other categories of motors in comparison with permanent magnet motors. Okay, they prefer PMSM because it is compact, efficiency is higher, the torque density is higher, all those things. So when we take an electric vehicle application, okay, if we take an electric vehicle application, there are few important parameters which would govern the choice of electric vehicle application. So some of the parameters that we'll consider are, one is what we call it as the size has to be compact. Other, the torque density is again an important parameter. Okay, torque density and efficiency. Efficiency of the motor is again an important parameter, and as well as other parameters like torque ripple, cogging torque, all play a very important role. So there has been a constant exploration of different kinds of motors for these EV applications. Okay, and we'll throw light upon all these things in the offline mode, wherein we'll discuss about all these categories. So this is a general classification of motors, and all these motors are being constantly explored. And for academic purpose, there has been a lot of scope for work in the design and control of these aspects of electrical motors. So that is the thing. And as I said, there are not only for EV applications, there are wider applications of electrical motors, so that we all know, right from a small toy car motors to all the mixers and grinders. All the applications will involve electrical motors, and all these motors are driven by certain constraints, or what we call it as certain performance criteria, wherein we try to explore different configurations of electrical motors. So it is not limited. The point that I am trying to convey is it is not limited to electric vehicle applications. It can be explored for a lot of applications, and these are some of the applications just I have listed. For if we take a BLDC motors, it is used in home appliances, it is used in printers, it is used in industrial equipments, automotive is what we are discussing, and then control, building controls and medical equipment. So all these things, BLDC, or what we call it as permanent magnet motors, are being preferred for all these applications. And this structure is very important. So we have, whenever we say it is a drive, whenever we call it as a drive, the control plays a very important part. The control aspect plays a very important part. The power electronics, the power converter interface, what we call, it plays a very important part. The motor, as we discussed, plays an important part. And if the load is nothing but what are the applications that we are going to consider, plays a very, very vital role. So there has been a lot of development in the area of development of control algorithms, or what we call it as how to have a programming logic, how to optimize the development of controller. And there has been a huge development in this particular area. And as well as there has been a huge development in power converter topologies, the power converter devices, which has made this particular area of EV, I can say, as possible, right? So when we see the structure of the controller, like a DSP controller or FPGA, whenever it is going to be mounted in an electric vehicle application, it has become very compact, right? So thanks to the advent of the digital logic circuits, and when even as I said, the power converters also have contributed a lot for all these development. So there has been a widespread exploration in the control aspect, in the power converter aspect, and the motor newer topologies of motor are also being constantly explored. So this has led to the development of compact drives for a lot of applications. So that is one particular aspect. So when we take a drive as a whole, it comprises of a controller, it comprises of power converters and motor coupled with the load. And especially when we take a EV application, okay, these are all the probable academic works that can be explored for academic research applications. Okay, the utility side, there has been a lot of work which is going on, and the control aspect, there has been a lot of work, and machine design, sensorless estimation. So all these are probable academic research areas which can be taken up for pursuing the research aspects. And whenever we say EV applications, whenever we do a simulation, we need to integrate it with the drive cycle. So this is what we call it as a drive cycle. So whatever, this is what is a representation of Indian drive cycle. So this we call it as a Indian drive cycle. So whenever we do a simulation with respect to EV for any motor, the load characteristics, or we need to give this particular drive cycle as input and see whether the performance matches with this particular drive cycle. So this is again a very important aspect. So we need to see whether the controller design matches with the drive cycle. So for every country, there will be a drive cycle. What is meant by a drive cycle? So what will be the acceleration time? What will be the nature of movement of electric vehicle in Indian roads? So that is what is depicted here. And whenever we design the controller, it should be able to meet these requirements of the Indian drive cycle. So that point we need to keep in mind whenever we are working on the simulation aspects of electric vehicle. So this is a general introduction. And when we take generally, okay, we come to the aspects of faults now. When we take electrical machine faults and condition monitoring system, right, again the classification. So the fault that can be classified into three categories. One, we call it as the electrical fault, other we call it as mechanical fault, and the third one is what we categorize as fault because of some external devices. Fault because of some external devices, right? This orientation they have given it for the other things. So the mechanical failure, bearing failure, drive mechanism, all those things, right? So whenever we take the electrical aspects, we need to have an eye on the stator part, eye on the rotor part, eye on the commutator and brushes. This is a general classification. And similarly, when we take the case of mechanical aspects, the air gap eccentricity, shaft, bearing, gearbox. So all these things are the possibilities of fault. And we can also expect a fault from an external device as well. So like this, we can categorize the fault, and we need to have a corrective action whenever there is a fault occurs. Okay, to ensure a reliable operation of the drive, we need to take a corrective action. So we know the effects of fault. Why fault diagnosis is very important. Fault diagnosis is important. Not only fault diagnosis is important. What remedial action? We need to diagnose the fault, and then we need to take a remedial action. So that is more important. Okay, we need to take a remedial action. So what are the variations? Because of fault, we get unbalanced voltages and line currents. We have increased torque pulsations, the average torque decreases, reduction in efficiency. So these are all some of the drawbacks of the fault. Now, how to do this? How to diagnose a fault? Because we assume that the motor is under running condition. Okay, the motor is running, or we assume that the electric vehicle is running. Right now, whenever there is a fault occurs, how we are going to identify that there is a fault? So that is going to be a challenge. So what sort of techniques we can use? So what we tend to do is we have a signal measurement. This signal, what is this signal? This signal can be current. It can be voltage. Okay, it can be voltage. We can have a speed signal, or we can have the torque variations like this. It all depends. Or it can be some sensors which are mounted on the machines. So we first measure the signals, and based on the signals, we need to identify whether a fault has occurred or not. So we need to monitor this signal. So that is what we call it as condition monitor. What we tend to do is we tend to monitor these signals, and then if there is a fault, okay, we should identify what is the type of the fault. Because only when we know the type of the fault, we can go for corrective action. So that is very important. So analyzing whether there is a fault or not is one thing. The second thing is what is the type of fault is very important. So we need to understand what is the type of fault. So that is why all these lot of machine learning algorithms are coming into play, right? And then we need to take the corrective action. So based on the fault, we need to take the corrective action. So this is the general thing that we will be discussing in today's session. So what sort of signals are there? How can we measure the signals? And from the signals, how can we identify whether there is a fault? Okay, if there is a fault, we can go for corrective action. So this is how it is done. So that is why we call it as it is a condition monitor. So when we take the electrical machine fault diagnosis, so we have motor fault types. Okay, again, as we have seen, motor fault types can be mechanical faults, eccentricity and coupled gear faults, bearing fault. These are all the faults. And electrical faults, we take it as a stator fault and rotor fault. Generally, suppose we have some Hall sensors for rotor position estimation, we can also make it as a Hall sensor fault, because Hall sensors are required for estimating the rotor position for all the so-called special electrical machines, or what we call it as a non-classical motors. The Hall sensors play a very important role. So now, how are we going to diagnose the fault? How are we going to diagnose the fault? So there are two things that the literature says. One thing is what we call it as invasive techniques. Other thing is what we call it as non-invasive techniques. So what is this? Invasive techniques and non-invasive techniques. Now, when we take non-invasive techniques, what we tend to do is we do not have we can have it as we do not have a physical sensor, a special sensor which will identify the fault. Okay, it will be mostly based on current signature analysis. Okay, the sensor, we can treat it as the sensor is not mounted on the motor itself. Okay, here we sense the motor current. Here we sense the motor current with the help of current sensor, right? And we do some sort of analysis. We do some sort of analysis and identify whether there is a fault or not. So that is what we call it as non-invasive technique. So what is non-invasive technique? We employ current sensors, right? And we take the current and we see, and we do some analysis and we see whether there is a fault occurring or not. What is invasive techniques? We have some sensors which is fitted on the motor, and we see whether there is a variation in the output of the sensors, and then we detect it. Of course, for this also we require all these analysis, wavelet analysis or S transform analysis we require. Okay, but we have sensors to be mounted. Sensors are mounted. Okay, sensors are mounted on the motor, and from the motor, what we tend to do is we take all these values. What are these values? These are all instantaneous values which will change with respect to time. Please understand, while we measure the values, the major challenge in the fault diagnosis is all the parameters that we take, either it is an invasive method or it is a non-invasive method, or varying with respect to time, will vary with respect to time, because fault can occur in any instant of time. So all these parameters are varying in time. So when it is varying in time, it's a challenge how to detect whether there is a fault or not. So that is going to be a major challenge. So we can employ the sensors specifically for monitoring the vibration, monitoring the temperature, monitoring the sound. They have included some chemical analysis as well. Okay, and the vibration analysis. And from these values, they will get all these values constantly. And from these values, we can say whether there is a fault or not. Right? How we need to process these values. We need to process by simply looking in the waveform. We cannot say. Okay, physically, if you see the waveform, we will be able to say. But the system has to predict whether there is a fault occurred or not. So that is going to be a major challenge. So these are all the fault diagnosis techniques. Right? Now, how to do this? So when you say, they say there are two methods of fault detection. One, they call it as model-free method. Other, they call it as model-based method. Okay, suppose we develop a model and we give the inputs and see the variations in the output. So that is what we call it as a model-based method. Model-free method, directly they go for hardware, take the data, and then they do it. So they classify into two categories. One is model-free method, other is the model-based method. Okay, whether we can simulate that particular model in MATLAB and take the values and see what happens. Like this, we can do. It is called as a model-based method. Or if we don't want the model, we can also go for model-free method. So that is what we call it as detection. Okay, fault detection and diagnosis, in the sense, what is the type of fault? There are two things, as I said. One is fault detection, assuming that there is a fault, and the second one is diagnosis. What type of fault? So for this, they go for classification methods or they go for reasoning methods. They go for classification method, they go for reasoning method. So this is what we call it as fault diagnosis approach. So please understand, there are two approaches. One, we need to detect the fault. And if a fault has occurred, we need to diagnose the fault. We need to diagnose the fault. So that is going to be the second step. And the third one, we need to take the corrective action. There are three steps. There are three steps. One, detection, diagnosis. The third one is correction. How are we going to correct the fault? So this is the procedure. So for this, they have devised some methods. So what is model-based method? Now, what is model-based method? So in a model-based method, what will happen? They give an input. Okay, there will be a model, there will be an actual system. We'll give the inputs to these systems, and based on the output. So this will predict the model, and this is the actual output. Based on the output, we can make a decision whether the fault has occurred or not, or some decision we can make. So that is what we call it as a model-based method. This is what we call it as a model-based method. Right? Two methods will be the same inputs will be provided depending upon the output from both the models. So we'll be able to train it, and we'll be able to make a decision using some algorithm. We'll be able to detect. So that is what we call it as a model-based method. Okay. And model-based for fault detection, the qualitative model-based, they classify into quantitative model-based. So here it is based on some knowledge. Okay, if this parameter is greater than this, okay, then they have some decision tree like approach, trend analysis, or casual models, or hierarchy based models. Because once the inner loop, outer loop, we say this current has to be greater than this current has to be greater than this, then it is a stator fault, stator A phase fault. Like this, you can have some analysis, and then qualitatively you can have it, and we can see whether the fault has occurred or not. The second method is what we call it as a quantitative method. Okay, wherein we estimate the parameters using filters or computational intelligence based method or statistical values. We take some statistical values, and then we see whether the fault has occurred or not. So this is what we call it as quantitative methods. So either we can go for a qualitative method, or we can go for a quantitative method. So this is the method of fault detection. Similarly, we can also predict the fault in electric drives. We can also predict the fault in power converters. So this I can call it as power converters. So far we have seen about the motor part. So similarly, if there is a fault in power devices, okay, the possibility can be a capacitor fault, or a IGBT fault, or a diode fault, or a controller fault itself. A controller can misfire in the sense there will not be any output from the controller itself. So that possibility also we can take. So that is one more type of fault which can be occurring in this particular drive as a whole. We can have this type of fault. So these are all the different power semiconductor devices fault. So how to detect the semiconductor fault? So how to detect the semiconductor fault? Again, we have model based algorithms, or we can go for signal processing based methods. Signal processing based methods in the sense we sense the current, and based on this we have a time domain analysis, and we have a frequency domain analysis. From this we take the values and see whether there is a fault or not. So this is one type of method which we can adopt, okay, for analyzing the semiconductor fault. So far it is generic. So far we can assume that we have discussed it for induction motor as a whole. But generally, when we take other type of machines, especially permanent magnet machines, when you take permanent magnet machines, so in addition to the conventional faults in the stator, okay, we can also have a magnetization problem. We can also include that. And as I said, we can also include the Hall sensor part. So that is also that. So we can have a short circuit fault, open circuit fault, unbalanced circuit, eccentricity fault. Like this is conventional. And apart from this conventional thing, we can include a Hall sensor fault or magnetization part. So this is with respect to fault in permanent magnet machines. So as we are predominantly using permanent magnet motors as well as induction motor, what type of parameters we can take for each and every category of machines, I have just illustrated. So this is the approach for a non-invasive method. This is the approach for non-invasive method, right? So from this is what we are going to carry on. I am going to give a demonstration of this aspect. So what we say, so we sense the three-phase voltage, we sense the three-phase current, we sense the flux, right, from the motor. We give it to a signal conditioning circuit. Okay, because we need to eliminate the noise from the circuits. And this data sampling is very important. How frequently we are going to sample the data. So we take the voltage, we denoise it or we filter it, right? And then we sample, or the sample itself is the first part. Sampling is a very important part. We sample it. Okay, because we'll take 1,000 samples first, or we take the sampling frequency as 1 kilohertz. Just for example, I'm saying 1 kilohertz, right? So for every 1,000 values, we'll see whether we'll monitor the parameters. Okay, and then we estimate. And this step is very important, is what we call it as feature extraction. Now, what is this feature extraction? This feature extraction will say whether there is a fault or not. There is a fault or not. Okay, so simply to understand, I'll give a simple example of what we call it as a feature extraction. Now, how do we remember different things that we see in our day-to-day life? How do we remember our friends that we see in our day-to-day life? We understand, or our brain recognizes the features of that particular person. So he'll be tall, he'll be having a curly hair like this. So those are the features which characterize a particular person. Similarly, when we take a current input from the motor, what we tend to do is we tend to take the features. Now, what do you mean by features? Features are used to characterize that particular signal. So when we see the features, we'll be able to identify whether a fault has really occurred or not. So that is a very important step. So that very important step is what I call it as feature extraction. So what is feature extraction? We take the current signals, okay, and we extract the features from the current signals and say whether there is a fault or not. What are the features that we extract? It depends on the algorithm that we are going to use. It depends on the transformation technique that we are going to use. Because I cannot, we can just take the RMS value or peak value. All those things are okay, but it will not correctly classify the fault. When there are more fault, there is a chance that it is missing. So in addition to RMS and peak value, we need to take some more features that will characterize the fault. So that is very important. So that stage is what we call it as a feature extraction. And based on the features, what we tend to do? We tend to do the classification. And from the classification, the next thing is decision making. What we tend to do, whether we want to stop the motor or whether we want to, we have a reconfigurable switch. So all these things takes the next part. So this is the technique that is predominantly followed for diagnosing the fault. Right? For invasive method. So for invasive method, what we tend to do is we take the vibration signals. We have a segmentation. We have a statistical feature extraction. And here again, feature extraction plays a very important role. Whether we go for an invasive technique or whether we go for a non-invasive technique, both the techniques will involve what? Both the techniques will involve feature extraction. Right? Here we physically mount a sensor. And take it. But whereas there we take it from the current value itself. Right? We can go for a hybrid combination. We can go for a vibration signal and we can also go for a current signal to have a better classification of a fault. So this is what we call it as a invasive method. We physically mount the sensors. So what are the steps? We have a data collection part. We have a feature extraction part. So from the feature extraction part, we go for fault detection and we go for fault diagnosis. So these are the steps. So where do we collect the data? We collect the data either from hardware or through simulation. We collect the data either from hardware or through simulation. And then we give it to where? We extract the features and then we say whether there is a fault or not. Okay, so the data collection is very vital. The data, as and when we have more number of training and testing set data, the output will be accurate. And one more thing, the simulation model that we built, it should also be accurate, and that should match with the hardware. So that should match with the hardware. So that is very important. Only then we can implement these algorithms and see whether it is really able to detect the fault or not. So these are the steps. And the next thing is, whenever I say I want to extract the features, it is a time varying quantity. It is a time varying quantity. So when we go for a time varying quantity, the frequency of the signals will also change depending upon the fault and occurrence of fault. So generally, we go for time frequency analysis. Generally, we go for time frequency analysis for predicting the fault. Please understand, this method can be applied for any application. Okay, I have taken an electric vehicle application and I am illustrating this. The same procedure you can also follow for, suppose if you are working in microgrid, you can also extend it for any other thing. Also you can use it. Okay, suppose you are using a solar PV system or a wind generation system and you want to monitor whether there is a operation is proper or not, you can also always apply all these techniques for those applications as well. So we go for a time domain analysis, we go for a frequency domain, or we can go for a time frequency domain. But for this, as it is varying with respect to time and frequency of the signal is also bound to vary, we tend to go for a time frequency analysis. And how do we do it? We have a data collection, we have feature extraction, and based on the features, we use some classifiers. These are all called as classifiers. We can use neural, we can use fuzzy, we can use expert system, or we can use a simple decision tree. Okay, simple decision tree algorithm is also sufficient, but the accuracy has to be checked. Okay, that is also possible. So we can also go in for these methods. So these are the methods for fault, I'll say fault classification. These are the methods for fault classification. Right? Okay. So now I'll just go into a few examples. Okay, and then we can have a break. In between, any clarifications, if I want to, I'll just stop for a while. Okay, and then I'll just check if there are any things, any suggestions or any clarifications. I'll pause for a few minutes. I'll leave the floor open to the audience. Okay, thank you. So if there are no queries, I'll just try to proceed. So what happens is, so we have taken a simple system, okay, wherein we take a BLDC motor, we have a battery, we have a 3-phase inverter, BLDC motor, and we have a current controller, which is used to provide the gating signals for the BLDC motor. Now, what we have done, there are different types of fault that can occur here. Okay, one we can call it as a single switch fault or open circuit fault, double switch fault, short circuit fault. It can be a lot of combinations are there. And similarly, whenever we take a sensor, okay, there might be a fault that occurs in the sensors as well. So there might be a fault that occurs in the sensors as well. So these are all the things that we can consider in the case of a BLDC motor drive. And as I said, there are different time frequency analysis technique. Okay, either we can go for a Fourier transform or short time Fourier transform or wavelet transform, or we can also go for a Stockwell transform. Generally, they prefer either a wavelet transform or Stockwell transform. Okay, and there are also other methods that we call it as a Hilbert transform. So Hilbert transform also we can use it. So these are all some of the methods that we can use to extract the signals. Why all these methods are used? These methods are used to extract the signals from the waveform. So this is what I say. Whenever I apply S transform, whenever I apply a Stockwell transform, S transform, okay, I'll get a value. What input I'll give to the S transform? I'll give the input current. Okay, I'll give the input current to the S transform. This S transform will process the input and it will give the time, it will give a matrix. It will give a matrix. This I call it as a S matrix. It will give a matrix. I'll call it as a S matrix. And from the S matrix, I'll extract the features. Okay, I'll extract the features. This I have, we'll have a demonstration, the second part of the session, wherein you'll be able to understand this. So I take the features F1 and F2. For example, I'm naming it as F1 and F2, and these features are nothing but the mean of the maximum amplitude plot. These are all the output from the S matrix. So I take the features F1 and F2. For simplicity, I have taken these two features. Now, what we tend to do is under normal condition. This is the motor running under normal condition, right? So their Hall sensors pattern is like this. Hall sensor pattern is like this, right? And we extract the features under normal condition. So see, under normal conditions, F1 value is 0.94, F2 value is 0.048. We take IA, IB, and IC. We take these stator currents, IA, IB, and IC, and we extract the values. Now, this is the waveform. Now, what happens is, suppose when there is a fault, we'll assume that there is a failure in the Hall sensor. There is a failure in the Hall sensor. Some electronics is in problem, and there is a failure in the Hall sensor. So when there is a failure in this Hall sensor, okay, what happens? The output from the Hall sensor becomes 0. The output from the Hall sensor becomes 0. So what will happen? There will be a deviation in the waveform. So see, there is a deviation in the A phase current, there is a deviation in the B phase current, and there is a deviation in the C phase current. So when there is a deviation, what happens? The value of the extracted features will change with respect to a single phase failure. When there is a failure in a single phase, what will happen? The features that I extract, this is what I said, it is used for characterization. The features that I extracted will change. So when the features that I extracted changes, we can say the fault has occurred. Who will say, I need to write a program and I need to monitor these features and find out whether there is a deviation from the original value. If there is a deviation from the original value, I can say there is a fault. What type of fault? If the value is in this range, it is a single Hall sensor failure. It is a single Hall sensor failure. The value is in the other range, I can say it is a double Hall sensor failure, right? When there is a double Hall sensor failure, see, the value is changing. When there is a double Hall sensor failure, the value is changing. So either I can go for a simple decision tree algorithm, or I can go for some machine learning classifiers to say whether there is a fault or not. So these are the features, and the feature values are changing when there is a fault. So how do we do this? So we initiate a closed loop control of BLDC motor. Okay, we analyze the stator current waveform. We apply S transform and extract the features. See if the observed value is equal to the actual value. Okay, or we can say obtained feature value is equal to the actual feature value, right? So what will happen if there is not equal? Okay, is not equal. What we tend to do, we have the identification. We go for the routine. So this is how generally a fault identification and fault classification is done. Generally, a fault identification and fault classification is done. This is one approach. See what I do, how it is implemented. So there will be a master controller, right? So we get the waveforms and we write an algorithm for S transform. The S transform features will be given to a master controller, and it will say whether there is a single sensor fault or whether there is a double sensor fault. So while we implement in hardware, we need to implement this. We need to extract the features. And then we need to classify whether it is a single sensor fault or whether it is a double sensor fault. So this is how a fault diagnosis is carried out in a BLDC drive for a Hall sensor failure. Similarly, the same approach, we can also use it for a switch reluctance motor. Okay, since we have taken this, this motor is also widely used for electric vehicle applications. So the same concept, we also apply it here. We have a AC source, which is we convert it into a DC, and we give it to a power semiconductor device, which is used to drive the SR motor. And we sense the signal, sensor signal, we sense the speed, and we give it. Now, suppose when there is a fault, see what happens. Phase A, phase B, phase D, there are 4 phases. And under fault condition, there will be a variation in the waveform. There will be a variation in the current waveform, voltage waveform, and the torque waveform. So whenever there is a variations in the waveforms during open circuit and short circuit. We'll take those waveforms, and what we tend to do is we take the phase current. We can apply here. We have applied Hilbert transform. So here we have applied a Hilbert transform. Hilbert transform is one more time frequency analysis technique. I'm not going into the detail of it because it's a general approach for the fault diagnosis, and then we extract the features, and then we can say whether the fault has occurred or not. So this is one thing. So see, we have taken different conditions. One is under normal condition, one is normal condition, what we have taken, and open circuit fault. See, there is a variation in the parameters. So the way there is a variation in all these parameters for different kinds of faults. So we can say when the value of F1 is changing to 0.5, then we can say it is open circuit fault. Suppose if it is 2.5, we can say it is a short circuit fault. Like this, we can have a decision tree algorithm, and we can find out what is the type of the fault. What is the type of the fault? So this is one thing. Or suppose when we want to use another algorithm, okay, then we can also take a speed. We can also input speed. One thing that I have said is we can use signals, or if we can extract the images, that is also possible. And then we can go for some deep learning methods for classification of the fault. So we can take the image as well, and then we can process that image, and then we can classify whether there is a fault, whether the fault has occurred or not. So that is one more technique. So that is what that is the another technique for fault diagnosis. So either you can take the signals, or you can take the images. We can take the speed images, and then we can classify the nature of the fault. So this is another technique. So these are all the techniques. I think I'll just stop with this. The machine learning part, the classification part, I think we can have it as after a break. Okay.
As per the schedule, we are going for industrial visit by 1 p.m. So before that, we have lunch in the college itself. Lunch, if anyone need non-veg, so if you inform, we can arrange it. Thank you. Sir, Balaji sir.
Yes, sir. Shall I continue, sir?
Yes, sir.
Okay. So now I'll just make a small video presentation, and we can see how the features are extracted. Okay. Sir, is it visible? Can you just say, are you able to hear participants?
Yes,
Now,
sir.
okay, we will discuss how to extract the features using S transform and Hilbert transform. So I'll take first a general sine wave, and we will see how to extract the features of the sine wave, and then I'll take a sag wave, and then I'll take a swell, and I'll show how the features will vary. Once it is over, we'll proceed to how to extract the features in the same way as per the BLDC motor that we have used in an electric vehicle, or any motor you can use, any induction motor or any motor you can use the same procedure. So as I said in my lecture, whenever we want to identify a fault, there are two steps. The first step is we need to extract the features. The second step is we need to classify what kind of fault. So we are in the first stage. The first stage is feature extraction. So for this, first I'll take a simple sine wave. Okay, first I'll generate the sine wave for simplicity. These are all the initialization instructions. So what I give, I initialize the value of t. I give the limit for t. T varies from 0 to 0.5. Okay, this is the time interval for t. And I'll just say v is equal to 0.2 into sine omega t. So, and then I say the plot command. So when you see this, we will get a normal sine wave. So this is the waveform of a normal sine wave. Now, the algorithm that we are going to use should identify this as a sine wave. The algorithm that we are going to use should identify as a sine wave, this as a sine wave. So what we will do is, this is a time varying waveform, or we can say the waveform varies with respect to time. So we need to apply a transformation technique, and we need to extract the features that will characterize this waveform. We should get numerical values that will characterize the waveform. Okay, we can take the RMS value of this, but when we have more number of features or more number of waveforms, then RMS value might not be a good indicator. So we'll go for the transformation techniques, S transform, and we'll go for a Hilbert transform. We'll go for transformation techniques. So we'll see how to see or how to use the transformation technique. So I have stored the values in a variable called as V. Now I am going to apply an S transform. So to apply the S transform, okay, I have a pre-written program. Just 1 minute, it will open. I have a pre-written program. See, the program is open here. So this program, okay, which is available in MATLAB, will give the S transform features. So for this, what is the input? The input is going to be my waveform. Here I have taken it as a sine waveform, right? And I need to extract the features. So this I have written a program called as new ST. Okay, you can have any name. So there are two programs. One we call it as a new ST, okay, which is used to extract the features. Okay, here I have written a subprogram. So what I do is I take the S matrix. ST stands for S matrix, T stands for time, F stands for frequency, and I give the name or the input value as V. V is my sine wave. So when I execute this particular program, it will in turn call this ST. It will in turn call this ST, and I'll get the features. So this F1, F2, F3, F4, F5, I have taken 20 features. We'll get the values of those 20 features. So that is the first step. So what is the first step? I'll give this program new ST. I'll give new ST. So when you see, this will take the S transform, and here we'll get the features. We'll get the F1, the F10, because it is arranged like this. Like this, I have initialized 20 features. I'm not going into the details of what features we have used. So I'm not going into those details. So these are all the values. So for example, if I take for a particular sine waveform, here the magnitude we have kept as only 0.2. The magnitude of sine wave we have kept as 0.2. If you see the plot of the waveform, you will be able to see. So F1 value. So what is F1? F1 is a maximum of time amplitude plot. So S matrix will return both two values. One is time as well as frequency. So first four features represent the time amplitude plot, or we call it as a time maximum amplitude plot. So I'll write it here. I'll just for understanding purpose, I'll get write the value here. This is a normal waveform. Okay, I'll give the different magnitudes here. I'll say here 0.2, and here I'll say 1. Okay, 1 in the sense the magnitude is higher. So what is the value of F1? Here F1 is 0.1. How do we calculate the F1? We calculate F1 by applying S matrix from the S matrix. So F1 is 0.1. Like, okay, or we can also type it here, F1. Then F2. Okay, what is F2? F2 is 0.0995. Okay. Or I can say it is 0.1. F2 is 0.1. Okay, that is also 0.1. F3 is for some waveform the features might not change. F3 is again 0.1. Okay, that is why we take more number of features. Right. F4, I'll take F4 is almost equal to 0. So the first four features I'll take. If you want, you can also say F5. So like this, we extract the features for each and every waveform. So F5 is 0.5. So Fi, I'll put it as 0.5. Fi, I'll put it as 0.5. So this is for a normal waveform with amplitude 0.2. Now what will I do is I'll clear this. Okay, now you can also get a normal waveform with a higher amplitude. So I'll just take this and I'll put it as 1. And I'll just say I'll just first plot it. I'll plot this waveform. So when you plot this waveform, so now we have a higher amplitude. So this is also a normal waveform. Right? Why we are doing this exercise is because it should differentiate the normal condition and maybe we can call it as a sag condition or a swell condition. So this is not a swell. So it is a normal waveform, okay, which is a sine waveform. So what will happen is even for a normal waveform, when the amplitude varies, what will happen? The features values will vary. So that is why we take different waveform as inputs, okay, and we train the machine learning algorithm. So here again, for a normal waveform, I extract the value, I do the S matrix, and I calculate the value. See here now, this is a normal waveform. Even though it is a normal waveform, the value of F is 0.5. F1 is 0.5. We'll see the value of F2. So F2 is also 0.5. F3 is 0.5. F4 is 0. Fi is 0.5. So these are all the values. So what does differentiating all these things are 0.5? Right? So how the machine learning algorithm will work? It will check whether if the values are in this particular range, then we can classify them as a normal condition. See here it's all is 0.1, Fi is 0.5 both the cases, whereas F1, F2, F3 values will change. So this is for one amplitude, I'll call it as a normal condition. Normal condition. So what are these things? These things are what we call it as features, which characterize the waveform. Now to make it more clear, what I'll do is I'll take a sag waveform. I'll take a sag waveform. So in a sag waveform, again I'll say, I'll first generate a sag. So this is the syntax for generating the sag, right? When you see the waveform, you'll be able to understand. So I'll generate a sag first. Let's say CLC. I'll generate a sag. Okay, so plot V. So I'll generate a sag. So see here it is, sorry, this is a swell, sorry. So this is a swell. If I want to have a sag, what I can do is this value of V, I'll just change it and I'll just change it as 1 minus. If I put 1 minus, it will be a sag. 1 plus, it will be a swell. So I'll say plot V. So we'll have a sag. So here the sag occurs here. Okay, sag occurs in this particular instant. Now this waveform has to be recognized as a sag waveform. So what will I do is I'll see what are the features for this sag waveform. I'll again say new ST. So it will calculate the values. So see here, we'll see 0.5. So I'll take it as a sag waveform. F1 value is 0.5, right? So I'll take F2. F2, see here, F2 is 0.3. F3 is 0.45. Now you can see the difference. F2 is what is the value? I'll just check it. So F2 is 0.3, F3 is 0.45, F2 is 0.3, F3 is 0.45. F4 is F4 is 0.07 and Fi is 0.3. So see here for a sag waveform, for a sag waveform, F4 is 0.07, it is 0.3. So see what happens for a sag waveform. In a sag waveform, what happens? The values changes. So this will characterize the waveform as a sag, right? Because there can be many sags, in the sense the amplitude can vary, the instant of time can vary. So we can have the sag occurring at different instants of time. So that is why we require a time frequency transformation. So the sag can occur anywhere in the start, anywhere in the middle, or it can occur anywhere. So we need to keep on continuously sampling the values and we should extract the features. And based on the features, the machine learning algorithm will say whether it is a normal waveform or a sag waveform. Now I'll take one more example. I'll take a swell. As I said earlier, I'll just so I'll say clear all. The same thing I'll take. So I'll take a swell. So I'll generate a swell first. So I'll say plot V. So now see here the same thing, the swell has been generated. Now for this, if I apply, we'll see what happens to the features. So we'll get the features. So see here, F1 is 0.7. So F1 is 0.7. F2 is 0.5. F3 is again 0.55. So 0.5, 0.55, 0.5. It is 0.55. And F4 is same value, and 0.07, 0.3. So 0.07, and it is 0.3. So here there is a difference. Okay. So that is why we take more number of features. So what we do, what we have done, first we have done a S transform. And to that S transform, what we have done is, we have extracted the features. We have first generated a waveform, and we have extracted the features. And we will see what are the features that will come for different waveforms. Likewise, we need to generate a data set. So this is one transformation technique, which we call it as S transform, which we call it as S transform or a Stockwell transform. So if you see this program, I'll take the S transform, and the value of S matrix will be stored in ST. And I do a calculation, which is mostly mathematics based calculation, and I extract the features. So what are features? Features are used to say what, or it is used to characterize the waveforms, which are used to characterize the waveforms. Okay, so this is a set of program that it has been written, and features are extracted. I say here, for example, I have taken 20 features. Not all the 20 features will be required. You can optimize that as well. So that is one more separate part. So this is one part of it. There is one more time frequency transform, which we call it as a Hilbert transform. So that also we can use, right? So that also we can use. That I'll just say, so you have a sag waveform here. You have a sag waveform. I'll apply a value here. So again, I'll plot V. So we'll get the waveform. We'll get the swell waveform. Okay, we'll get the swell waveform. Now to apply a Hilbert transform, okay, what we can do is, I'll just say S1, or I'll say H1 is equal to Hilbert of V. V is my waveform, Hilbert of. So see what happens, the Hilbert transformation will be generated. So what I need to do is, I can, this consists of a complex value. So I can extract the real values. I'll say AB absolute of Hilbert of V. Right, I'll now say plot of H1. It's a plot. So see what happens when I plot it. So this will represent, there is a swell here. See, in this portion, there is a swell. The other portions are normal at 1. So this is one thing that we call it as a Hilbert transform. So now how to characterize this? To characterize this, again I can take the features. I can say mean of H1, mean of H1. So mean of H1 is 1.0597. So this is one technique. So what is the Hilbert? This we can extend. We can have some more features, and you can characterize the features corresponding to that particular wave. Now the same thing, we'll just take up one more example. I'll take a swell. Sorry, I'll take a sag. I have taken a swell now. Now I'll take a sag. So when I take a sag, I'll just say plot. I'll just give the value. I'll say plot of V. So now there is a sag waveform. So for this sag waveform, what I'll do is, I'll take the Hilbert transform. Now I'll say plot of H1. So see here, there is a marked difference between those two waveforms. The first swell waveform, what we saw was there was a swell, but now here there is a sag. So there is a dip here. So there is a dip here, right? So it means that there is a variation here. Now, if I take a mean of this particular value, if I take mean of H1, so it will be different. It is only 0.9, indicating that there is a swell. Right? You can also make different instance of sag and swell. So here, the value that we have given is A is 0.4, 1 plus 0.4. It means that it will be 1.4. Here I will say it starts at 0.16 and it will end at 0.24. For example, I am saying. So I'll generate a different instant of swell. I'll say clear all just to show the difference. Right? Since we saw the swell sag waveform, I'll just take it as a sag itself. Now I'll take plot of V. So when I take plot of V, see here now there is a variation in my instant where the sag occurs. So now if I take the Hilbert transform this, see what happens. I'll just take the Hilbert transform. I'll plot it. So when I plot this, see what happens. The instant will change. But we'll see what happens to the mean. We'll see what happens to the mean value. But the mean value also has changed a little bit. So depending upon the time at which the fault occurs and depending upon the magnitude of the fault, the features will vary. So the features are used to characterize the waveform, characterize each and every waveform. So this is the basic. So this is what we call it as a feature extraction. Now, when I give these features as input to my classification algorithm, we will be able to classify the nature of the waveform. We can say whether it is a sag, whether it is a swell, or whether it's an interruption. Like this, we can say. The same principle we are going to apply for a BLDC motor or for any motor. So what I have done is I have taken a MATLAB model, okay, which is already available. For simplicity, it is already available. I have taken the same reference, right? So this is the model available in MATLAB just to show how a fault can be created and how you can characterize the fault. So in a BLDC motor, I use an inverter, which is used to drive this BLDC motor. And these are all the measurement parameters. I have a Hall sensor, and a Hall sensor will be given to the gate signals, which will in turn trigger the gate pulses. It will trigger the gate of the inverter. So this is the normal flow. So I have a Hall sensor. Based on the Hall sensor, the triggering of pulses of the inverter is going to take place. So depending upon the speed reference that I give here, as per this particular example, the input voltage is varied, right? Or you can also have a PI controller and you can also do it. But here they have used a PI controller for the changing the source, but we do not usually do this. We'll sense the current and we'll just change the gate pulses here, right? So that is one method. But I have taken a model which is already available in MATLAB itself. So when you execute this is under normal condition. This is under where I have changed this. I'll just show. Yeah, this is compiling. Just a minute. So here I forgot to give one input. So we need to give that input. Okay, sampling time I have not given. So I'll give the sampling time TS as 5 e power minus 6. So now it will work. So I have given this as input. So we'll see the output waveforms. So when you see this is the speed, we have given speed as 3000. Sorry, I think I have not changed this here. 1 minute. So here to introduce fault, I have made a change. So I'll just remove that as well. So now it will work. So we'll see the normal operation. So when you see here, this is the stator current, back EMF, rotor speed, all these things we are sensing. And this is the normal current waveform. This is the normal current waveform for A phase. This is for B phase. And the other thing is for C phase. And we also get the torque and speed. The torque and speed. Right? This is the torque and speed. Okay. They have given a step input. Initial value is 0. The final value is 3. So that is why there is variation in torque. Right? So now we want to analyze some fault which is occurring in the inverter. So first we need to take this particular waveform and characterize the features for a normal operation. What are the features that are there for a normal operation? Only then we can characterize the fault. Right? I'll just enumerate the procedure. So this waveform, I have stored it as a variable. As a variable, I have stored as I1. The same procedure I am going to apply. That is why I explained the S transform previously. So now the variable is I1 here. What I do is I just see the value of I1. I1 is stored in I1.signals.value. I1.signals.value. So when you see this, there are totally 5,000 values here. There are totally how many values? 5,000 values here. So here, that is why sampling plays a very important role. So this has to be a continuous process wherein we need to sample the signals. I'll take first 1,000 values. So I'll say V is equal to I1 dot signals dot values of 1 is to 1,000. I'll take the first 1,000 values. Now I'll plot this V. Okay, I'll plot this V. So when you plot this V, I'll get this value. Okay, I'll just get this waveform. So what I'm going to do is I'll apply the S transform for this particular value. So I'll get the features. See, F1 is the value, F10, F2. So F2, I'll just take it. F2 is 1.3140. F3 is 1.3140. F4 is 0. F5 is 0.5. So like this, I take the values. This is for a normal waveform. Right? For a phase current A. Okay, you can also have for different phase current, you can get the values as well. Now suppose I am going to introduce a fault. Okay, for introducing a fault, you can make this as a individual switches and then you can also introduce, but I am giving a simple procedure. See here, I am giving 1 to where? To the first device. So the first device, what I'm going to do is I am removing the signal, and the first device, I am going to keep it permanently on. It is not going to be on off. It is going to be permanently on. Right? It's going to be permanently on. So now I'm going to simulate this. So when I simulate this, see the current characterization. So the current value will change because it's like I'm keeping it permanently on. It's like short circuit, right? So when I take this particular value of current, stator current, see what happens. I'll take the first 1,000 values again. I'll take the first 1,000 values. Now I'll take new ST. Okay, it is better to clear this and then you do it. I initialize first TS as 5 e power minus 6. I'll just run this. So this is under fault condition. So what I do here is I'll just take the value of V as 1,000 values. I'll take new ST. So see what happens. So here, see here, the value of F1 is 18. So it has jumped to 18. So it means that there is a fault. And the fault can occur in one switch or the fault can occur in multiple switch as well. So that is why we go for machine learning algorithm and we go for more number of features to accurately classify the fault. Right. So here again, the value will see F2 is 18, F3 is 18, F5 is 0.5 because F5 does not change, F4 is again 0. So like this, each and every value is going to change here. So which will characterize the fault. One more thing I'll do here, instead of permanently turning on, I'll permanently turn off this, right? It is like open circuit. So that switch will not be triggered at all. So what happens? So here, this is the output. Now again, I'll repeat the same thing. What I do is, I'll take the, it's better to say run again. I'll just say clear all. I'll just say CLC. I'll just initialize TS. So now I'll run it again. So what will happen? I again take the first 2000 values. I'll take new ST. Now if you see the values is different. Now it has become 1.6186814. Similarly, F2 is again the same value. This is 0, F4 is 5. All the other values are same. Right. So depending upon the waveform, the features value will change or it will be same. So like this, what happens now? I have made an open circuit. So there is a distinction between a short circuit that is permanently making the switches on, permanently making it as an open circuit, and a normal condition. So what we need to do? We need to prepare a matrix like this, right? And it should have the waveforms at different time instance. One more thing is very important that we need to do is the fault can occur at any instant of time. So here I can couple a time and say that only during a particular time there is a fault. So for this, we can have a step waveform like this thing, and we can also say when it becomes 0 and when it becomes 1. Like this also you can say. You can give a step input and vary the time of instant of fault. So here we are assuming that the fault occurs directly when the motor starts itself, the fault occurs. But that might not be the case. It might be under normal operating condition, but after some time, what will happen? The fault might occur. So we need to take care of that condition as well. So a large database is required. Why a large database is required? Because the fault can occur at any instant of time, right? And a fault can occur in any particular phase, right? Or one phase or two phase, and the time can vary. And the load condition can also vary. So you need to incorporate the variations in load. You need to, because when there is a variation in load, the current waveform will change. Right? The current waveform will change. The speed value will change. So like this, you need to take the variations in the load as well, variations in the time as well. And then we need to vary the instant of fault, and then we need to generate a database. So if we have all combinations in the database, then the fault classification will be accurate. So what will we extract from here? We do different simulations and we incorporate different conditions of fault. And what database we take? We take a database which has features and which has a classification. This table we need to prepare. This table is very important. What does this table give? This table gives the relationship between the feature, the values, or we can say the features and the condition. Conditions in the sense a normal condition, a no fault condition, like this, the condition. So here you can incorporate, here I have taken only current. You can also have a speed waveform, right? You can also have a speed waveform, or you can also extract the values from torque as well. Suppose you want to have a vibration signal. So then you can also have a vibration signal as well, right? So you can add n number of variables, but all these variables are time varying. So since we are operating with a time varying variable, we require a particular transformation technique to extract the features. It need not be a S transform. It need not be a S transform. So as we discussed, okay, you can also take a Hilbert transform as well. Okay, you can also take a Hilbert transform as well. So I'll say TS here just to illustrate this. I'll run this program. Okay, you can also apply a Hilbert transform, and from the Hilbert transform also you can take the values. You can take the values. So see, I'll again say the values here. I'll say the command. I'll say the command h1 is equal to Hilbert of absolute of v. Right. So I'll say plot of v. So this will give a plot indicating that it is a decreasing one, because I have made it as 0, because the value we have given at the gate is 0. Now we can also take the Hilbert transform. So what we can do is we can take the Hilbert value, mean of h1. So mean of h1 will be 0. Now if I introduce it as a permanent 1, okay, then if I keep it as 1 itself, so that again there might be a change. So there is a variation here. So what I do here is, it is better to clear it. I'll say clear all. I'll initialize this, and now I'll again simulate it just for. See what I'm doing? I'm again taking the first 1000 values and Hilbert, and I'll say plot. So this, see the way there is a change in the nature of the waveform because it is permanently 1. And now if I take the mean of Hilbert transform, the value is changed. So likewise, for different fault conditions, you can extract the features, and these features will form an input to your classification algorithm. This is the first part. So I have explained how to extract the features using the feature extraction technique, namely time transformation technique, time frequency transformation technique, namely S transform and Hilbert transform. Next, we'll see how to classify this using the machine learning classifiers. That is the second part. Yes, I have made this presentation with the objective of showing things in MATLAB, how it can be actually done, such that you can have those already know it is okay. So if you want to work on this, you can have a real-time experience of how to do this in MATLAB, right? Any questions? I can take it, or else we can proceed. Any clarifications or suggestions in this aspect? Right. Okay. So if there are no clarifications, we'll proceed to the last part. So I have divided this into 3 categories. One is the basic theory part, okay, of how to have a fault diagnosis. The second one is the how to have how to have the database generated. Now we'll go to the actual machine learning part. Now how a machine learning classifier is going to work. I'll just take one more application of a machine learning classifier and I'll illustrate it. So that is the fault classification part. So generally, now we have understood that we have a database. So what is that we have? We have a database. So now what is there in the database? The database will have the features. The database will have the features, and what is the class? Okay, whether it's a whether it is a no fault condition, or whether it is a open circuit fault condition, or whether it is a short circuit fault condition. Like this, there will be different classes. So for characterization of each features, we'll have some examples. So we'll have some values. So we have this database. Now, once we have this database, we need to have a classifier. So for this, either you can go for a simple or conventional, what we call it as a artificial neural network approach. So in artificial neural network approach, there will be input layer, there will be a hidden layer, and there will be an output layer. So the features are given as input to the input layer, and then it will be processed to the hidden layer, and we get the output. The error will be back propagated, and all those things will be done. So we'll get the output. So either we can go for a neural network based approach, or we can go for a decision tree based approach. Now, what is decision tree based approach? In a decision tree based approach, it's like a lookup table approach. We have some if conditions. Okay, like in the previous example, we have some if conditions. So if the parameter f1 is within this range, then if parameter is between 0.5 to 0.7, if f1 is between 0.5 to 0.7, so then it will be a open circuit fault. Like this, we can have some conditions. So you can go for a decision tree based algorithm. So, or we can go for some algorithms like support vector machine. You can go for some algorithms like algorithms like support vector machine. So I'll just take up this support vector machine and I'll explain how to do this in MATLAB, how to simulate this in MATLAB, right? So any one technique you can adopt. So all these things comes under the machine learning technique. For a machine learning technique, we need to have a data, and we need to have a model, and we need to have a model that will be used to predict it. So we need to train the model. We need to train the model such that whenever we give an unknown data, what will happen? The output will be predicted. So that is required, right? So here we have different learning, what we call it as a supervised learning algorithm. We call it as an unsupervised learning algorithm. So in supervised learning itself, we have one thing which we call it as a classification. Another thing is what we call it as a regression. We have two things. One is classification and regression, right? So classification in the sense we are going to classify whether there is a fault or no fault. Or regression in the sense we say is if we are doing a simple addition program, so then we can call it as a regression. Addition, subtraction, like that, those sort of programs, we can call it as a regression. Unsupervised learning, we can go for clustering. Okay, we can go for some clusters. So these are all the general algorithms or learning algorithms that are available. So what we tend to do, the same thing. If we present an input, we'll extract the features, we'll classify them, and we'll get the output whether it is a car or not a car. In a deep learning, what we tend to do, the feature extraction as well as classification are built in a single stage itself. There is no separate feature extraction stage. So that is the main difference between a deep learning algorithm and a machine learning algorithm, right? So we'll take up a support vector machine. So support vector machine is one of the widely used algorithm for classification. So it is a supervised algorithm which is widely used for text and image classification, handwriting recognition, data mining, bioinformatics, and medicine. So we give the input as features. So whatever we have discussed so far is this. So we have extracted the features. So and once the features are extracted, we should give those features to a machine learning based classifier. We'll give this to a machine learning based classifier, and this machine learning based classifier will say whether it is a for what type of fault condition. So for this, what we tend to do, we need to train the network. We need to train the network to say the condition. So how are we going to train the network? For that only we have extracted the features. So what does SVM do? Suppose we have two classes. Assume that we have two classes, and SVM support vector machine will tend to find a hyperplane, or will tend to find this line which separates these two, which separates this class and this class. Whatever is represented as the lighter dots, I can say, is one class, and the darker dots is other class, or +1 and -1, right? So this denotes -1 and this denotes +1. So we need to find out the line which separates these two. So if we are able to find out the hyperplane, okay, then we can say whether we can say what type of class it is. Okay, if we give it the input, if this is in this particular range, we can call it as +1, or here you can call it as -1 or -1 or +1. So like this, we need to find out the hyperplane. But how to draw this hyperplane? So that is going to be a challenge. Now, what is the hyperplane that will actually actually discriminate these two classes. So we can draw a hyperplane like this, or we can have n number of hyperplanes. We can have n number of hyperplanes, but the thing is, we need to select the correct hyperplane that will be used to classify, or a line, a thin line we need to draw. When the values are the other side of the line, it will be +1. On this side of the line, it will be -1. So the major challenge here is to determine this particular line, which will optimally characterize the classes based on the features. And to aid this, we have some support vectors. So that is why we call it as a support vector machine. To aid this, we have some support vectors, which is used to have an accurate classification. So I'll take a simple example of how to give data to a support vector machine. So just a basic for understanding, we are going to assume that we are going to classify the fruits. We are going to classify the fruits as orange and apple. So we all know that it is a lighter weight one, orange, and the size we classify. So we take the weight and size as features. We take the weight and size as features, which we call it as a input data set. And we have a class, okay, which we call it as orange. So we have a orange and apple. So we can execute this in MATLAB with a particular syntax. So we have a syntax in MATLAB. Suppose we want to do this in MATLAB environment. Okay, I'll just show the command. I'll just so there is a command. What happens is svm train. So svm train, we give the input as training set. What we give the input to the svm? Input to the svm is the training set. Input to the svm is a training set. This is the data, or we can call it as a feature. This is a class. This will say when these are the features, when weight is 65 and size is 4, it is orange. Okay, when it is 66 and 4.5, it is again orange. When it is 70 and 5.25, it is apple. Like this, we give it. Right. Now, once we have this particular data, we can train it using this particular syntax, svm train, training set, group train, and we can show plot. Show plot is nothing but to show the plot. So see here, it has determined the optimal hyperplane. It has determined the optimal hyperplane, and it will store the parameters corresponding to this hyperplane. So once it is done, what we need to do is, suppose when a new input is coming. So when we are giving a new input, what needs to be done? We need to classify it. So what is the syntax for it? svm classify. Right. So we have created a svm structure. We have created a what? We have created a svm structure. How we have created a svm structure? It is based on training. So it is based on training. We created a svm structure, and for that we give a test set as input. So when we give an unknown input, it will tend to classify the unknown input as the corresponding. It will try to fit in. So that is what a classifier actually does. So this is how we can do it in MATLAB. But this is for a two-class classification. That is, there are only two classes here. So this syntax will work for a two-class classification. Okay. Either there should be only two classes. Only then we can draw it. But the problem is when there are more than two classes. Suppose whenever we have a fault condition, there will be more classes. Okay. There will be more than one class. So how to do that? So for this, before going to that, this is the general procedure. What we tend to do of how to have a machine learning classifier, we create a training set, we create a test set, we train the data using the command, we test the data and calculate the error, or what we call it as a accuracy. This we call it as a accuracy, right? So this is what we call it as a accuracy. So what is the goal of SVM? SVM will try to maximize the margin between the hyperplane. So this is the optimal hyperplane. How will it arrive? So it will try to distinguish. It will try to have a distance that will clearly tend to discriminate between the two classes. So it will tend to maximize the margin with the help of the support vectors. These are all what we call it as the support vectors. These are all the support vectors, right? So it will try to find the distance such that from this, if it is D, it will be able to classify this. Again, if there is a D, it will tend to classify it. So it is it. Now, when we have more than one classes, suppose we have more than one classes, what we do is we tend to map this two-dimensional to a higher dimensional feature space. Higher dimensional feature space. The original input space can always be mapped to a higher dimensional space where the training set is separable. Because when we have more than one classes, okay, it is difficult to separate it when we keep in only two dimensions. So we tend to go for a higher dimension space such that we'll be able to classify it easily. So that is the thing for multi-class classification. So that is the thing for multi-class classification. So what we tend to do, for this we have a kernel function. So this is a single thing, right? It is a 1D input. Now, when we want to go for a higher classification or better classification, what we tend to do is we tend to have a kernel function that will map a one-dimensional input to a two-dimensional value. Say I'll write a function such that y is equal to x square. So what will happen? I am trying to map it in a higher dimensional space. I'm trying to map it in a higher dimensional space. So we can have it. So like this, we can have a separable plane. When x is equal to this value, what will be the value of y? So when we are able to plot this, x is equal to 1, y is equal to 1. X equal to 1, x equal to 2, y is equal to 4. X equal to minus 1, y is equal to 1. X equal to minus 2, y is equal to 4. So like this, see what happens? I am able to have a separate value, and here I can determine the hyperplane easily. So whenever we are going in for a multi-class classification, we need to incorporate a kernel function. We need to incorporate a kernel function. So what is the purpose of kernel function? It will try to transform to a higher dimensional space. Okay, again, all these things are available in MATLAB. You can directly use it. You can have a higher dimensional space. Right? So we have some kernel function. So we have a linear kernel function. We have a polynomial of power kernel function, radial basis function. All these things are used for mapping. So I have also given a reference for this. So you can get it for a multi-class classification. So all these things, you can go for a multi-class classification. Either for a multi-class classification, you can go for a polynomial-based classification, or you can go for a RBF function. But generally, RBF function is a preferable method wherein it is used to map it to a higher dimensional space. Right. So once we do that, okay, how we tend to classify? Suppose we have 3-class problem. What we tend to do is we tend to analyze it. So there are 3 classes here. Okay, there are 3 classes here: green, blue, and red. Okay, so the thing that is done is, first it will take us 2. First it will classify x1 and x2. Then again it will take x1 and x2. But see here, the data that is taken is class 1 and class 3. So it is the data which is taken here is x1 and x2 are the coordinates. But see here what is taken. Here it is what is taken. Here we take green as well as blue. So here we take blue, and we take this. We can call it as the round and as well as square. We classify circle and triangle here. I will say like this: we take circle and triangle and draw the hyperplane. Here we take circle and square and draw the hyperplane. Here we take a circle and cross, and then we can draw the hyperplane. Like this, we can separate it. Okay, we can separate it, and then we can try to draw the hyperplane. So we take one thing and then we try to classify the rest. So like this, it is done. Right. So we convert it into a one versus rest. Okay, one versus rest, and then we try to classify it. So this is how we call it as a multi-class classification. So this is how it is done. Right. So to summarize how it is done, we have a motor. Okay, we sense the value, we give it to a hardware, right? We give it to the hardware part, we extract the values, and then we give it to a, maybe the program of S transform and classification can be in our system, and in this system we'll be able to classify whether there is a fault or not. Okay, we sense the values through the sensors, and we give the input through a serial port or through some port to the system, and we can assume that in this system we can have all the algorithms that we have discussed, like feature extraction, the feature extraction part, the classification part, we can have it, and then we can say what is the type of fault, and based on the type of fault, what we can do, we can take a remedial action. So this is how it is done. So this is how it is done, and this is the thing that I have discussed so far. Okay, for fault classification with respect to electrical machines. So we have analysis module, we have database, and we have acquisition module. So these three modules are very vital, right? So this is how it is done. Okay. Right. So what I have done is I have just touched upon the different kinds of machines which can be used for electric vehicle applications. Okay, and then how to extract the features, and then how to apply machine learning algorithms for two-class classification and multi-class classification problem. So this is the overall summary. Right. One more video I have prepared that for the want of time I'll share with Muttamilan sir so that you can see that. So in that video I have covered how to simulate the SVM part in MATLAB, so you can also make use of it, right? So with this I'm completing my session, right? Any clarifications or any suggestions, you are always welcome. Thank you.
Any queries? Balaji sir,
Yes, sir.
in inverter, how many level will be possible in hardware, sir? Multi-level inverter.
Multi-level inverter, we can go. It all depends on the application. So what kind of application you are going to use? We can go 7 level, 9 level, we can do it. But what is the motor or what is the type of load that we are going to have? And depending upon that, we can choose a proper level. So that is the thing.
Some told it is 9 level is possible.
Okay, okay, sir.
Can anyone have done above 9 level, sir?
See, we have provisions, sir, for above 9 level. But as I said, it all depends on the application. Whether it is really required or not, we need to study. And then we can implement it. It all depends on the application.
Okay, if 9 level is implemented, means what will be the THD, sir?
Why we go for multi-level inverters, as per the IEEE standard, it is the allowable is 5%. And when I say the THD, again, the THD depends on the type of load that we consider. If it is a resistive load, it will be well within the limits. But again, when I'm going to feed a brushless DC motor or for the application which has a more inductive load, so then the value might be better in comparison with the conventional value. So to actually see the THD, we need to simulate that particular load, and then only we can comment on the THD value. For a normal inverter, we need to simulate, and for a 9-level inverter, we can simulate, and then we can see the THD value.
Any queries? The above question is from Venkatesan G from Sairam Engineering College.
Okay.
Any
okay,
more
sir.
questions?
Okay, sir. If there are no queries, I thank you, sir, for the opportunity and for interacting with the participants for their patient listening. So thank you all the participants.
Yes, sir. Thank you. Once again, thank you for sir. It is a
Thank
very great and valuable presentation for us.
Thank
If
you, sir. Thank you, sir.
any seminar or whatever may be the thing which we need, we can call you for our campus, sir.
Thank you, sir. Thank you, sir. I hope the participants would have gained a takeaway from this. Thank you.
Yes,
Thank you
sir.
all.
Yes, sir. So the
Okay.
feedback link is posted in the chat box. Please fill the form, and after filling the form, you can leave the Zoom platform. Thank you all.
Thank you all. I leave the meeting, sir. Thank you, sir.
Thank you, sir. Thank you, sir.